Hi students, this is another video to discuss application of electrostatics. We are starting with a question which may be oftenly asked in the board examination. Question is, prove that there is no electric field inside the charge conductor. So we are going to do that with the help of a Gauss theorem. Let us take one charge conductor. This is a charge conductor in the form of a shell like a football whose surface is uniformly charged. Let Q is the uniform charge distributed over the surface. Capital R is the radius of the shell or the conductor or the hollow sphere, whatever you want to say. First of all, we will observe what is the electric field due to this charged shell at various points. Means outside the shell, on the surface, inside the shell, right? When we will find out the electric field inside the shell, right, automatically we get an answer that there is no electric field inside the charged shell. So I have taken one point outside the shell, right? From passing through that point, I have constructed a Gaussian surface in the form of a sphere. Take any area element. Let us say this is an area element whose area vector will be something like this. If I observe the electric field due to this shell, it will be in the same direction. So flux is E ds cos 0. Total flux will be E ds 0 to 4 pi. This is the area of the Gaussian surface. This total flux is E into 4 pi r the square. Apply the Gauss theorem. By Gauss theorem, this total flux is E into 4 pi r square is Q by epsilon naught. Result is Q by 4 pi epsilon naught r square, very similar to the result of electric field due to the point charge. The only difference is here small r, that is the distance of point of observation from the center of the shell. Now if I take this observation point on the surface of the shell, if I shift this point on the surface of the shell, now my Gaussian surface will be just touching this shell, but in the form of a sphere. It will be something like this. And I proceed in this similar manner. I will going to change the limits here. Small r will be replaced by capital R. This will be capital R. This will be capital R. Right? So on the surface electric field will be Q by 4 pi epsilon naught capital R the square. Likewise, if we are interested to find out the electric field inside the shell, so let us take a point here which is also at a distance. We can consider this distance anything x. I am taking it again r. Here small r is now less than r. When I considered the point outside the shell, small r was greater than capital R. Now again doing the same thing, I will construct a Gaussian surface passing through the point r in the form of a sphere. And if I apply the Gauss theorem, that is E ds is Q by epsilon naught straightwise. Since there is no charge inside the Gaussian surface, see here the total charge whichever is placed, that is residing on the surface of the shell. There is no charge inside the shell. When there is no charge inside the shell, this charge should lie inside the Gaussian surface. This total charge is 0, right? Inside the Gaussian surface charge is 0, so electric field is going to come out to be 0. So inside the charge conductor there is no electric field. On the surface it is similar like to the point charge, and if I take a point somewhere outside the shell, result is Q by 4 pi epsilon naught small r the square. Now we will draw a graph between the electric field and the distance from the center of the shell, right? See here, just pause a video for the moment and try yourself, right? What will be the shape of the graph between the E and the R? Let us draw, students. So I have taken one y-axis, one x-axis. On the x-axis I am going to take this distance small r. On the y-axis I am going to consider the electric field. So here at the center electric field is 0. It will remain 0 till we touch the surface of the shell. Up to this point electric field will be 0. Electric field will be 0. On the surface, E surface, just recall the result. It is Q by 4 pi epsilon naught capital R square. So on the surface it will be something like here, and this will be Q by 4 pi epsilon naught R the square, right? So when I go outside the surface, this R, E outside is Q by 4 pi epsilon naught small r the square. Electric field go on decreasing, right? E is inversely proportional to r the square, so it will go on decrease like this. It will be something like this, rectangular hyperbola, right? So this will be the variation of electric field with distance due to a charged shell, right? Now I am posing you a question. If instead of this charged shell we have a charged solid conductor, like we have a copper ball, solid ball, and which is uniformly charged, something like this. This is a solid conductor, charged conductor, and we calculate the electric field due to this charged conductors at various points, outside, on the surface, inside. Just try to think, will the result be exactly similar to this charged shell or not? Write down in the comment box, will the result be exactly similar or not? Let us discuss. We know that conductor has a very special property that whatever the charge given to the conductor, it will always reside on the outer surface of the conductor. It will not stay inside. This is the property of the conductor. It will travel and it will reside on the outer surface of the conductor. So if I consider this charged solid conductor, charge is not going to stay inside. It will come outside. So this whole charge distribution will be something like this, So no matters, it is exactly similar to this. So if we have a charged solid conductor or a charged shell, result of electric field will be exactly similar, right, due to one special property of the conductor. However, if we have a let us say we have a solid piece which is uniformly charged but which is not a conductor, or we can say there is a accumulation of charge in the form of a sphere, then the results will be different. For that, see my next video. Till then, goodbye.